So we're going to go over 4.3, domain and range graphically. And by the end of the lesson, you should be able to find the domain and range of relations and functions graphically. Now, a function is a special type of relation that pairs each domain value with exactly one range value. So if you guys remember, when we have a graph, you can have anything, right? That was actually not the best example. You can have anything on the graph. And for every one x, you only have one y, okay? So that's why it's a function. It passes the vertical line test, so there's only 1 point for each one. Yes? So they want us to give the domain and range of the relations. And give the domain and range, oh, this is a choice, okay. So we know that this is the x, and we know that this is the y. Now, for the domain and range, you always go in order. From least to greatest. So let's do the order. Now, for domain and range of this type of mapping and for dotted graphs, we're going to use this little squiggly line. I don't really know the name of that squiggly line, but I'm just going to call it the squiggly line. Again, going from least to greatest at the x, so it'd be 1, 2, 5, and 6. So I'm going to write 1, comma 2, comma 5, comma 6, little squiggly. Then for the range, we're going to do the same thing. We're going to start for the most negative. In this case is -4. And we're going to end up with 0, which is the least negative. So -4, comma, -1, comma, 0, comma. And we're going to close it with the squiggly. So again, for the table, we're going to use a little squiggly line to give the domain and range of the relation. So the domain, as we know, from least to greatest, squiggly, 1, 4, 8, and then the squiggly. Now for the range, we're going to go again from least to greatest. So we have 1. We have another 1, guys, but we're only going to use one of them, okay? You don't repeat it, neither in the domain or in the range.
If we do, it's wrong.
So we would go 1, comma, 4. And then you close it. So they want us to give the domain and range of this relation. But this is neither a a table or a mapping graph. So neither a table that looks like this, a mapping graph. So because it's neither, it's an actual graph with a line, we are going to write the domain and the range a little different. So we're going to use either brackets or parentheses. Now, what does the brackets mean and what do the parentheses mean? The brackets mean the endpoint is included, so the point is included. I'm going to erase the mapping and the table. Same as a dotted graph, so the point is included. And then for the parentheses, it means the point is not included. Not included. Now, keep in mind this is for domain and range only. So for the domain, when it comes to a line, you're going to go from the farthest left point to the most right. And you're just going to write the endpoint. Remember, for the domain, we only care about the x value. So the most left point x value is right here. And the most right point x value is right there. So again, we're going to write it from least to greatest. So we're going to write the most left point is 1 and the biggest one is 5. Now, because it's a closed circle, you guys should remember this from the inequalities. It's included, and an open circle means it's not included. So, closed circle, we're going to use a bracket. 1, comma, 5. Close the bracket. For the range, it's the exact same thing, except you're going to go from the lowest y value to the highest y value. In this case, the lowest y value and the highest y value are just one apart, but it would still be closed circle. So it's going to be a bracket. Then 3, comma, 4. Remember, domain is always x and range is always y. Those values. Next slide. Given the domain and range of the relation, tell whether the relation is a function and explain. So guys, I'm going to keep the range in green and the domain in blue just to kind of keep it color coordinated. Obviously, you guys can tell this is not a function. As it says it at the bottom, nearly all domain values have more than one range value. And also, it doesn't pass the vertical line test. So it doesn't pass it for any point except for 2. So it's not a function as it doesn't pass the vertical line test. Now for the domain. Remember, the domain is always the x value. So the most left x value is right here. So the farthest left point is that one. And the most far right point is this one for the x value. So those points are going to be -5 and 3. So since it's a solid line, we're going to use a bracket, -5, 3. I'll explain why we're going to use a bracket because it's a solid line after we do the range. And then for the range, we're going to look at the most high point, which is this one, and the most low point, which is that one. The most high is 1. The most low is -2. Again, we're going to write from the least to the greatest. So it's going to be bracket -2, 1. Now, why did we use a bracket and not a parentheses? Remember, bracket means included, right? Now, also, a solid line is included. The parentheses is excluded. And an excluded line would be dotted. You guys won't have to deal with the dotted line until we start graphing inequalities, but it's just good to know and get your dip your toe in the water just a little bit. So let's look at example A. They want us to find the domain and range of the function represented by the graph. Now, for A, they want us to write the order pairs, identify the inputs and outputs, the domain, and the range. So, this is a dotted line, so the domain and range is going to be with the squiggly line. So I'm going to start with the domain, and I'm going to write the squiggly for the range. The domain, remember, is the x values, so it would be right here, right here, right here, and right here, highlighted in blue. So going to be from the most left is going to be -3, then 0, then, sorry, not 2, 1, and 3. And for the range, remember, it's going to be right here in green, the one that is with the y-axis. Most negative is -2, then 0, then 2, then 4. Remember, those are the domain and range. Now, the order pairs are always written as x and y. That's always the case. That is the coordinates of where the point is. So this point right here is at -2 on the x and is at -2 on the y. This point right here is at -1, 0, because we only move left once and we don't go up. This third point is at +1 because we move to the right one, that's towards the x, and then we move 2 up, so that means it's 2 for the y. And the last point is 3, 4, again, x first, y second. So we found the domain and range for the first one. We wrote the order pairs, and they want us to identify the inputs and outputs. The inputs are always the x's. So we can say the inputs is a domain, and the output is the y, is the range. Now, if you were to have it on a quiz or a test, I would prefer for you guys to actually write the numbers, -3, 0, 1, 3, and -2, 0, 2, and 4. For right now, I just want you to understand the inputs is the x and the outputs is the y. So for B, we have identified the x and y values represented by the graph. So the x and y values would be these 2 points, so the endpoints of the graph. That's the order pairs you guys are looking for this question. So for B, they're asking for those order pairs. So for the most left one, we should get -2, -1. And for the most right one, we're going to get 3, 2. So for the domain, remember is the x value of those points. We can actually, even since we wrote it from left to right, we can just see the x values are those 2. And since it's a line, we can do a bracket, -2, 3, and be done with the domain. And for the range, again, is the y's of each of those points. So if you don't have a graph and you know those are the 2 furthest points up and down, which is the same case right here, we would put, sorry, I didn't change it to a pencil. We will be putting for the range a bracket, -1, 2. Again, the inputs are the x and the outputs are the y. In this case, since it's a line, we will put input x, so it would be the domain again. And the output, just because I'm running out of space, it's the y. I'm just going to use the pointer arrow. It's the y, so the range. So let's give the domain and range of this relationship. The domain, again, in this case, we are going to use a bracket. And for the range, we are going to use a bracket. Now, this might not be a function because just in pass the vertical line test, there's more than one output for one input. But it's okay because we're not looking if it's a function or not. We're just looking for the domain and range. The most left points and right points I highlighted in blue, and the most up and down points I highlighted in green. So the domain would be the blue. It would be from -3, 2. And then the range will be -2, 4. Okay, so functional notation. As it said, this is just for functionality, but I will explain to you how it works. So an equation that is a function may be expressed using functional notation. The notation f of x is read as f of x represents the variable y. So you guys are used to seeing stuff like this, right? This is something that you guys are used to. Now, all this is doing is this f of x is going to replace the y. So it's just going to be f of x equals 3x plus 7. All this means is this is a function. You can input x and get y values out. You can do that at any point with the original anyway. It's just when things get more complicated and you have a bunch of problems and a bunch of solutions that you have done, this is the easiest way for you to know what you inputted and what you got out to make sure you're correct. I will explain it to you in the next slide. So for example, you have y equals 2x plus 6, and that can be written as f of x equals 2x plus 6. All they did again was grab this y and input the f of x. That's it. I'm going to use a highlighter instead of the pencil. The y and the f of x. Now, given the equation y equals 2x plus 6, evaluate when x equals to 3. Now, the way you guys have always done it is like this. I'm just going to rewrite the equation first. Plug in the 3 into the x, right? 2 times 3 is 6 plus 6, and y equals to 12. That is how you've always done it. And with the functional notation, you're going to get the exact same thing. I'm going to rewrite this equation with an f of x right here. Now, if I plug in the x equals to 3, I'm going to write f. And instead of x, it would be of 3, close parentheses, equals 2 times 3 plus 6. The reason I wrote it in blue is because I want you guys to notice, wherever we plugged in the x right here, we also plug the x into there. Now you're going to solve it the same way. F of x equals 6 plus 6. And then we're going to get, f of 3 equals 12. Now, we got the same answer right here and right here. So you can solve it the way you want, and you can always, like the way you've been doing it, and then just plug it in after into the f of x, or in this case, f of 3. The reason I like using the functional notation is because when you get, like I'm repeating myself, to higher problems and you're solving for a lot of different points and a lot of different things, you know right here you plugged in a 3 for an x and you got a 12 for the y. Here you just got y equals to 12. You don't know what you plugged in if you for some reason lose your work. You know what I mean? Or it gets messy and you're not able to follow it. This is why the functional notation is great. So you guys don't have this in your PowerPoint, but these two questions are from last night's homeworks. This is how you're going to tell from a, let's say, not a graph, a table, how you're going to tell if it's a linear function or not. Linear functions are constant change, okay? That is what you're looking for. Constant change. Now, how do you figure it out? You realize from x0 to x1, you're just adding 1. From 1 to 2, you're just adding 1. From 2 to 3, you're just adding 1. So that's a constant change on the x. Now on the y, we're adding 2. We're adding 2. And we're adding 2. This will be a linear function because it's constant, okay? Same here. This is plus 1, plus 1, plus 1. And then right here, it actually happens to be plus 1 as well for the y. So it doesn't have to be the same number as long as they're consistent within the y and within the x. That's how you're able to tell if it's a linear function based on a table. So how do you identify a linear function in a graph? So I'm going to draw two graphs right here to the best of my abilities. A linear function is a straight line, whether that be up, down, left, okay? So all of those are linear functions. What is not? So yes, straight line. If it's a straight line, it's a linear function. Equals linear function when it's a graph. If you get anything else other than a straight line, a V, a squiggly, that, and whatever you may get, this is not a straight line, so it's not a linear function. All right, so this will be it for this section, the notes. You can go ahead and start your homework. You do have homework.